All right, let's go ahead and start. So we were talking about hypothesis testing last time in the symmetric case. So remember, the setting here is your quantum system is prepared in one of two states, rho or sigma. And then your goal is to guess which one is prepared. And, there are at least two ways to measure error probability. One of which is what we previously did. That's symmetric hypothesis testing, where you take an average of the two errors and minimize that. The other is called asymmetric hypothesis testing. That's what we'll do today. So this is where you place a constraint on one error probability and then minimize the other probability of error subject to that constraint. Okay, so called asymmetric hypothesis testing. I think it also goes by the name of Neyman-Pearson setting, after some statisticians who looked at the classical case of this. Okay. So you're given a quantum system prepared in the state rho or sigma, and then the goal is to guess the state. Okay. How do you do so? You perform a measurement. So it's a binary measurement. We'll call it M and identity minus M. If you get the outcome M, it means you're guessing rho. If you get the outcome identity minus M, it means you're guessing sigma. So there's two kinds of error probability. We already talked about this, but just consider this a review. So the type 1 error probability is the probability you guess sigma, given that the state prepared is rho, and the type 2 error probability is the probability that you guess rho when in fact sigma was prepared. Okay, so in the setting of asymmetric hypothesis testing, we're interested in this kind of quantity. So it's often denoted by, often in the statistics literature, this is called alpha and beta, okay? Type 1 and type 2. Okay, so then you can define this operational quantity, which is what we discussed. You place a constraint on the type 2 error probability. Sorry, on the type. Right, let me just write it and then I'll explain. So first you fix epsilon, which is some number between 0 and 1. Okay, and then you're trying to minimize the type 2 error probability subject to this constraint and the type 1 error probability. And you're minimizing the overall measurement outputs. Right? So that's the problem. And you can think that there's this kind of trade-off curve space. So here's epsilon between 0 and 1. And this also goes from 0 to 1. So here's beta epsilon. And I'm trying to remember if this curve is convex or concave. It goes one way or the other. All right, I'm just going to make a guess. Just go with it. Anyway, you can think of this as like some delineating some kind of trade-off curve for the error probabilities. Also, what's nice about this quantity, this is a semi-definite program, right? We're minimizing over positive semi-definite operators subject to this constraint. The M is less than identity, so that's a measurement operator, and also that this type 1 error probability is less than epsilon. So this is an SDP. This is the primal SDP. And you can use these tools that we've talked about to calculate the dual SDP. Let me try to locate this. Sorry, I didn't have it in my notes. It was a little hectic. Yes. All right. So you can use what we learned about semi-definite programs to work out the dual. So the dual SDP. So you'll have it. So rather than a minimization, it's going to be a maximization. And you maximize over all scalars that are non-negative and positive semi-definite Z. The objective function becomes this right here. And then what do we know? We know that from strong duality, well, okay, we know that they're equal. And why is the dual useful? Well, if you're only interested in getting lower bounds in this quantity, then you can play around with values of mu and z, and any value of this objective function for mu and z being this constraint is a lower bound, right? So as far as an interesting research question, you know, a number of people are interested in bosonic Gaussian states. Very interesting question that has not been addressed in the literature is if rho and sigma are Gaussian states, what can we say about this quantity? What is the optimal measurement operator? It's likely not going to be a Gaussian measurement. That's the usual kind of thing that's found. And so the thought that collaborator and I had was to play around with the dual and try to make some guesses, you know, get bounds and so on. Yeah. Right. So you're saying when epsilon is 0,
Yeah, because
then you're not allowing yourself any error at all, right? And I think the optimal measurement operator is the projection onto the support of rho. That's a known fact. I don't remember the simple way of proving that off the top of my head. You can see that it works, right?
so that's
Oh no, it's not necessarily going to be 0. More often than not, it's going to be 1. Yeah. So you know, okay. Let's look at an example. So this is what we're discussing. What about the case when you allow no error probability for the type 1 error? Then you can pick m equal to the projection onto the supported row. So like, if you can write rho like this, the projection onto the supported row are the values of I for which pi is strictly greater than 0. That projection, right? And so you can see that it satisfies the constraint. It's a legitimate measurement operator. And, you know, the trace of this is 1, so this implies the trace of 0. Okay. And then that leaves you with the value of the objective function. Okay. So if you pick states in a random way, you have to pick, well, okay. Let's just say this. If rho is full rank, then this value is 1, right? Because if rho is full rank, the projection onto its support is the identity operator. And, but you know, you didn't allow yourself any wiggle room for this error, right? There's like a trade-off. Oh, I see. My plot is wrong. That's what you're saying. It should be like this. Thank you. That was your underlined message. All right. Good. So the claim I'm making without proof is that this choice is optimal. Like we showed that it satisfies the constraints. But we didn't prove optimality. I don't know how to show that quickly off the top of my head. I think we might have done that in the book. What's that?
Trace of m rho has to be 1, where m has to be the projection of the support. Also military.
No, it could be the identity operator. It can include stuff outside the support of rho, and it contributes 0. Right? Okay, good. So last time we learned about the data processing inequality. This is something we're going to be focusing on a bit in the next few lectures because we're going to start introducing distinguishability measures. Okay. And whenever you have a distinguishability measure, you look for data processing. So what we're going to do is define a quantity called hypothesis testing relative entropy. We're using the name relative entropy. I believe we haven't introduced that term yet. You can just think of this term as, in a very broad way, as meaning that the quantity obeys data processing. Later on, we'll introduce, in fact, in this lecture, we'll introduce what is called quantum relative entropy and show a relation between hypothesis testing relative entropy and like the standard quantum relative entropy. Okay, how we're going to define this, write it like this. H for hypothesis testing, D is for relative entropy or divergence, and then epsilon is the same epsilon over here. So what you do is, this is a probability, right? And you take the negative log of that probability, and then it becomes like an entropy. Data processing inequality is this statement that under the action of a channel on no states, this hypothesis testing relative entropy does not increase. Okay. Last time we proved data processing inequality for the error probability in symmetric hypothesis testing. How did we do that? We had an intuitive reasoning that, you know, if you have rho or sigma, there's some box prepared in the state, and then you do a measurement. That measurement will be described by M and identity minus M, and it leads to some outcome probabilities, two of which will be these. All right, and then here in this quantity, you see we're optimizing over measurement outputs, right? So there will be some choice of a measurement operator M, which corresponds to a measurement with M and identity minus M, that will be optimal for this quantity, okay? And then data processing says, well, if before you do a measurement, you do a channel, and then you do a measurement, that's suboptimal, right? Like, unless the channel is the identity channel or a unitary channel, more generally an isometric channel, okay? And then we had a detailed mathematical proof to show why the error probability followed data processing. Well, you could follow a very similar proof to make this conclusion. So this time I won't do it. All right. Are there any questions about this reasoning? There's a funny picture in the Nielsen-Chuang book that explains data processing. So it's like, this is rho and this is sigma. It's just kind of figurative. And it's like, yeah, that's rho and sigma. And then a channel could be, this is again figurative. A channel could be like, you just cut out the bottom part. And so then, you know, under this channel, you can't tell whether the state is smiling or frowning. They become less distinguishable. So data processing is about distinguishability. Like something is lost under the action of the channel. And when we thought about a channel, we thought about something lost to the environment under a unitary interaction. Right? So under the channel, these states are no longer distinguishable. And in general, they become less distinguishable. So that's what data processing is saying.
Is it possible to make them more?
It is impossible to make them more distinguishable. Yes. You can think of, you know, and people have used these data processing inequalities to come up with different ways to prove the second law of thermodynamics, right? It's like a fundamental limitation. And in all of this business of more generally quantum resource theories, one of which is thermodynamics, data processing of distinguishability measures is always at the center. Yeah. So you can view it as some kind of fundamental law. Do you have a question?
No, I was just going to ask, because this sounds kind of similar to something we did. I think we showed something like that.
Unitary evolution, entropy remains invariant under unitary evolution. But if you do more generally open system dynamics, then entropy can increase.
That's what it was. We had introduced the environment, and this seems kind of similar because channels aren't unitary.
In general, a unitary evolution is a special case of a ground channel, but not vice versa. Good. Okay, so that's some background on this. This is often called a one-shot distinguishability measure, because it's like if you're trying to distinguish rho, it's like one copy of rho from one copy of sigma. Now we're going to do something information theoretic, or similar to what we did last time, is considered the asymptotic scenario. Okay. And this is something called Clonestein's lemma. So why don't we keep a memory of this quantity in the corner. So you have it. So now we're going to argue for Clonestein's lemma. I'm not going to give you a full proof. It's, it takes too long. But the full proof is there in the book. You're interested. We will need the data processing. We'll make a little note of it. Okay. So the Clonestein's lemma is a statement about the asymptotics of this quantity. Just for clarity, let me rewrite this equation slightly. That's the relation between them, right? It's obvious, but still. So dh epsilon is like the error exponent for the type 2 error probability. Right? When we studied the Chernoff bounds, we proved that the error decays exponentially fast with a certain rate, and that rate was equal to the quantum Chernoff divergence of two states, right? So now we're going to show something very similar that if we take tensor power states and do hypothesis testing, then the error decays exponentially fast with the number of copies. And again, we want to identify what is the optimal error exponent. Okay, so that's the topic. That's the topic of Clonestein's lemma. And again, it's named after a classical person who had nothing to do with the quantum physics. Which is how it goes. So the statement is this. If we plug into this hypothesis testing relative entropy tensor power states, then here you should really imagine that the experiment is like this. Omega is equal to rho or sigma. You don't know which one. And then you have n copies of the unknown state available. You're allowed to do a collective measurement on all the copies and then decide rho or sigma. So that's the game. Okay. And Stein's lemma shows this beautiful result that this optimal error exponent is the quantum relative entropy. And it's given by this formula. Okay, so the non-degenerate case is when this is the critical formula. Okay, and in this class we're always thinking qubits, so we use binary logarithm. Okay? It doesn't really matter for this setting in terms of an error exponent. It's just the way that we find everything. We could have used natural log and e to the minus dh, and it would have been fine. All right, and so what does this theorem say I mean, you can reinterpret this statement as saying that beta epsilon, rho tensor n, sigma tensor n, goes like 2 to the minus n relative entropy. That's roughly what it's saying. And there are two parts of it. You know, to prove any equality, typically you have to show two inequalities. You have to show the left-hand side is greater than the right-hand side. The right-hand side is larger than the left-hand side, larger than or equal to. Okay? So it's saying two things simultaneously. One is that, you know, in the limit of large n, there exists a measurement operator. There exists a sequence of measurement operators, call them Mn and identity tensor n minus Mn. So there exists some measurement that can achieve this as the error exponent. That makes the error, the type 2 error probability decay at this rate. So that's one part of it. That's the achievability. But in Shannon's theorem also, there were two parts, the achievability and the converse. The achievability is where you show the existence of some scheme. The converse is where you say you cannot do any better than that. So that's the other part of this. If you have some measurement operator such that the type 2 error probability is decaying faster at a faster rate than the relative entropy, then you can conclude that actually the type 1 error probability is converging to 1. That it's going very bad. Okay? So that's the other side of this. That's the converse part. So, you know, the statement is that this decay rate is achievable by some sequence of measurements. And it is optimal. Okay. And then also what the theorem does is it provides a concrete operational meaning to quantum relative entropy. I'll just abbreviate it as QRE. Okay. So like we had in the quantum turnup bound, there was a connection between an operational task and a distinguishability measure. Very similar thing going on. Okay. This distinguishability measure is kind of like at the foundation of all of quantum information. One of the goals of the book is to show how all these different operational tasks boil down to entropies, and then essentially all of those entropies can be understood in terms of quantum relative entropy. Okay, so it's like a parent entropy from which you can get others, and we'll get into that later. Okay, so this is a really important theorem. This was a little bit of history. In 1982, there was a proposal for a formula for quantum relative entropy. Let me go back farther. If we have probability distributions P of x and Q of x, the classical relative entropy is defined like this. Okay. And this is also called the Kullback-Leibler divergence, after some statisticians. I believe this was 1951. And then, you know, Shannon later used it in the context of information theory. I don't know the years of when Stein proved the classical version of this statement. Okay, so given this formula, you might wonder, okay, well, what is the quantum version of that? Right? A decent and interesting question. In fact, that's like the base, one of the basic questions behind all of quantum information. Like we have some task that was considered classically, and what's the quantum version of it, and what are the associated information or distinguishability measures. So when you see this formula, you might wonder, okay, maybe it's this. So like, take sigma inverted, that's like Q, right? So we're replacing P with rho, and Q with sigma. You see, okay, Q is inverted, so let's invert that. And if we do this sandwich, we get a positive semi-definite operator. And then we can take the logarithm of that, right? We talked about functions of matrices, so that's what we're doing now. And then we can have this. So I believe this is the formula that was proposed by two researchers named Wilde and Stashevsky in 1982. And so they thought maybe this is the right version. It turns out that, I think it was 1962, someone named Umagaki had proposed this one. Okay. So these formulas stood for a long time, 1962, 1982. I don't know if those are the proper years, but anyway, then in 1991, Dennis Petz and Fumio Kiai proved this result. And so this is what showed that this was the correct formula. The fact that it has this operational or physical meaning. That's sigma inverse. You'd invert it on its support. I mean,
On this board.
yeah. Is that all right?
And you can take on the rest.
Yeah. Yeah, so sometimes the support conditions for this are the same as this one. And in fact, I didn't write the support conditions here. Like this is only finite if the support of P is contained in the support of Q. Those are kind of the technical cases. So anyway, this 1991 work ruled out this formula. And, for many years, it was thought to be irrelevant, but then 2019. The problem is the archive paper says 2009. Right? I don't know. It's 19. Anyway, in 2019, people showed that this quantity is actually useful in giving upper bounds and capacitance. And then that forced Sumit and I to have to rework the book to incorporate details about it. Anyway, let me get to the point. So I think that's essentially all I have to say about all this. That the larger message is that anytime you have a classical formula, you might wonder, okay, what is the quantum generalization? In many cases, there could be an infinite number of generalizations, right? These are just two. There's all kinds of other things you could do, right? Like we could take sigma to the -1/2, sandwich by root of the 1/2, and then sandwich by sigma to the -1/4. And in the commutative case, it would still collapse through this formula, right? So the thing is, when you propose an information measure, you should at least look for it to obey data processing. So what Golovkin and Stashevsky did was they proposed this formula, and then they showed that it obeys the data processing requirement. And then it's thought, okay, maybe it could be useful for something. But to this day, no one has found an operational meaning for this quantity, other than using it as an upper bound in tasks like quantum channel discrimination. Okay, so let's talk about how to prove this. And to do so, I'm going to introduce even more distinguishability measures. So, today will be a whole bouquet of distinguishability measures. Okay. So classically, as a generalization of classical relative entropy, there is the Renyi relative entropy. Okay, and this is defined for alpha between 0 and 1 and 1 and infinity. Okay. What you can prove is that in the limit, as alpha goes to 1, for this d alpha, you get back the usual relative entropy. Get back this classical relative entropy. And that you can show using derivatives, L'Hopital rule, kind of thing. Okay. There are at least 2 quantum generalizations of the Renyi relative entropy. One of them is due to Petz. It's called Petz-Renyi relative entropy. This was introduced in 1985. And you look at this formula and you do exactly what you think should be the quantum generalization, and that's the Petz formula. Okay? So write it like this. So rather than the sum over x, we'll have a trace. And rather than p to the alpha, we'll have rho to the alpha, sigma to the 1 minus alpha. Right? This quantity has the property that it has the same property that when the limit as alpha goes to 1, it converges to the quantum relative entropy. Right? I'm going to be skipping that calculation today. We might return to it later. But that you can prove using L'Hopital. Okay. There's another generalization of classical Renyi relative entropy. And this is where I came in 2013. Some colleagues, we wrote a paper where we called it this, and then there was an independent group who kind of discovered it independently. So this is a different generalization of the classical formula, where instead of doing like the obvious thing with these to generalize the quantity, you do an operator sandwich. Okay? So the prefactor and the log are the same. You also have a trace. You take rho, you sandwich it by sigma to the 1 minus alpha of the 2 alpha. And then you take the whole thing to the power alpha. Right? And interestingly enough, it's not obvious. If you take the limit of this quantity as alpha goes to 1, it also converges to quantum relative entropy. All right, so let me write these things here. Quantum relative entropy. Okay, so both of them have that property. All right. And This is a proposed distinguishability measure. So what's the first question that we ask about the proposed distinguishability measure? Does it obey data processing? So this one obeys data processing alpha between 0 and 2. Okay. This one obeys data processing alpha between 1/2 and infinity. Okay, so what I want to do today is take as given some inequalities that relate hypothesis testing relative entropy to the Renyies, and then use those to prove the Clonestein sum. Okay, and I'm going to be hiding some details from it. All right, so any questions about any of this stuff so far? We've introduced a fair number of formulas. We've introduced hypothesis testing relative entropy, classical relative entropy, quantum relative entropy, the Wilde-Konstantinsky, which we won't use, classical Renyi, quantum Renyies. If you Google entropy zoo, there is a wonderful diagram that someone named Philip Weiss made, which shows all of these entropies and how they're linked to each other. Very beautiful, nicely laid out diagram. Maybe I can find that just to show you, then you'll appear on the camera. Oh, it's right here. Okay, so you see this? Welcome to the entropy zoo. Say hi to the audience. Okay. Good. So we'll first prove the upper bound. So to do so, we'll invoke a lemma. This is an upper bound on hypothesis testing relative entropy in terms of the sandwiched quantity. Right? So the statement is this. Let rho and sigma be states. Let epsilon be strictly between 0 and 1, alpha greater than 1. All right, so what is nice about this lemma is it gets you to, so you kind of know that you're, I mean, we gave the conclusion of the theorem. The goal is to get to quantum relative entropy. The bridge to get to that goal will be one of the quantum Renyies. Okay. Why are we shooting for that? It has nice properties. it connects to the quantum relative entropy via this limit. They also have an additivity property. Okay, so in this theorem, we're considering tensor products of states. So one thing you can check from the Pet's Renyi relative entropy is that it's additive. Just like entropy is additive for independent distributions. So this follows pretty directly from the definitions. So that's a very nice property, right? Because what we're going to be doing to get this upper bound is we're going to be plugging in tensor power states and then go into the remedies. Okay, so, but speaking more about this lemma, it connects us from an operational quantity to the distinguishability measure. And then over here, you have this kind of correction term. Which it cleanly separates out the distinguishability of the states and this epsilon correction term. There's a question of how do you prove this lemma? Okay, we're going to be invoking two lemmas today. This is the easier one to prove. Okay, the proof is in the book, actually just a few lines. What you use is data processing of the sandwich point for alpha between 1 and infinity. So you need that to start out with. But once you have that, you use data processing under measurements to kind of extract the type 1 and type 2 error probabilities. And then you can work with them in some algebra to get this inequality. You can make the measurement be the optimal measurement for this hypothesis testing relative entropy. Remember the definition of it here, minimization of all measurement operators. You take the optimal one, turn it into a channel, and then you use data processing of that channel, you rewrite, and you get this. Okay, so just leave it at that. But now I want to invoke it to show you how clean and simple the proof of Clonestein's lemma becomes if you have this lemma. So let's take this quantity. Plug in inequality. All right. So that's just plugging in. That's a basic, simple step. Next, we can use the additivity, right? So if we invoke we have this additivity. It holds for the Pet's Renyi, but also for the sandwich. Okay. I didn't say that, but this also holds for the sandwich as well. You just plug into the definitions and work it out, and you'll see it. What does that mean? This upper bound will collapse. You'll get the sandwich entropy of rho and sigma added n times, when you divide by n. So this just collapses to something that's nice. Okay. Now, the operational quantity of interest involves a limit as n goes to infinity. Okay? So we take the limit. And the assumption, alpha is a parameter we can tune. This inequality holds for all alpha strictly greater than 1. So, we'll make the assumption that alpha is strictly greater than 1. Take the limit as n goes to infinity. This correction term goes away. Right? So then we're left with limit goes to infinity. And this inequality holds for all alpha strictly greater than 1. Okay? So that's a very strong statement. Since it holds for all alpha greater than 1, we're allowed to take the limit as alpha goes to 1. Okay? So now, and then we get the desired result. Right? Infinity. So that's a simple proof of the upper bound. And that's called the converse statement. It's saying that there's no scheme that can achieve a higher decay rate than the quantum relative entropy. That's what the upper bound says. Okay. What was at the core of it was data processing. Why? That was the key tool that we used to prove, at least what I said is used to prove this inequality, data processing under the measurement. Okay. So that's a relatively short proof of the quantum Stein number, but we did skip steps. Okay. Any questions about this? Yeah.
It's not very important, but are we sure that the limit alpha goes to 1 exists? Because we have the expression only from greater values than 1. So
Yeah.
we need to prove that the limit exists from lower values approaching to 1.
So that's a claim that I'm making here. That this limit exists and it converges to the quantum relative entropy. That can be shown. But that's a good question. You have a question? Is it related to that?
So I think, yeah, I have a question. Something like what plus minus.
Converge to the same. Yeah, both converge to the quantum relative entropy. That's what this is saying, right? From below and from above.
Now it's like if we do like is there an order of this?
They are ordered. I haven't stated that. Yeah. So the quantum Renyi relative entropies are ordered alpha less than beta. We have this and we have this. I don't know if that's strictly needed for this proof. All that's needed is this claim. Yes. We were assuming, right, so here we're fixing epsilon between 0 and 1 and alpha greater in this statement. Okay? It's the order of limits is important. That's what's going on here, the order of limits. If you do the order of limits the opposite way, there's a blow up, but that's not the order that it's in. Okay? The order that we're taking is first this, then this. And then it's fine. So to review, we're fixing epsilon between 0 and 1 and alpha is strictly greater than 1. This inequality holds for all epsilon in those parameter ranges. Now we've shown this inequality. It holds for all alpha strictly greater than 1, all integers n greater than 1, epsilon strictly between 0 and 1. And then I'm saying the quantity of interest is to take the limit as epsilon as n goes to infinity. So we do that, and then this is gone. All right. The claim now is that this inequality holds for all alpha strictly greater than 1. then I'm allowed to take that. All right. So it's an order of limits thing. Okay. Good. Lower bound is actually going to be very similar. But there's going to be a fair amount hidden. There is a similar lemma which goes like this. All the sandwich ones go to the pretzel. And this is the lemma. This is the lemma, and this is the proof. So mathematically, it's identical, all right? But conceptually, what's going on is very different. So to get this lower bound, you have to devise a measurement that does, in terms of its error exponent, at least as well as the hypothesis testing relative entropy is the error exponent. Okay? So this now involves exhibiting a measurement with error exponent at least the hypothesis testing relative entropy. Okay. How do you prove it? There was a bound that we had the last time. Okay. This is a bound. This bound you can use to derive this lower bound. Okay. That's done in the book. It's an interesting proof, but like, I don't know how much you would learn from studying. It's just kind of a lot of manipulations to get from this operational quantity to this distinguishability measure. Okay. But that's the core message, that there exists a measurement that does at least as well as this, and then it's very convenient analytically because now you have this lower bound in terms of Petzerian, right? And then it's just using properties of Petzerian in a very similar way, and so then you get the lower bound. And that's really the proof of this, the quantum Stein's lemma. Okay, but the core message is that this is the operational meaning of quantum relative entropy. It's the main reason we use it in quantum information theory. In future communication tasks, the goal will be to get upper bounds and lower bounds on rates of communication in terms of hypothesis testing relative entropy. And rho and sigma will become density matrices related to a channel you're trying to communicate over. And then exactly this kind of thing to get lower bounds. That's how essentially the rest of the book is done for all communication protocols. I seem to be getting eaten alive by mosquitoes in here. Is anyone else? They just like my blood. All right. I have like 6 bites from this lecture. All right. Okay, we have about 20 minutes. Any questions about this? We're going to proceed to a new topic. Yeah.
So the the pets when you are is pretty ubiquitous.
It's pretty what?
Pretty ubiquitous. Like it's
Ubiquitous?
Yeah.
Uh-huh.
But the churn of the CEO of Blue given alpha,
Yeah.
those are not really as common.
Well, I mean, the Pets Renyu is embedded in it, right? Remember, the Chernoff quantity is this. And so, you could rewrite it, right? 1 minus f. Yeah.
Does that mean the asymmetric setting is more natural than the symmetric setting?
How is that?
Because one can be expressed as the other. A special case of the other.
I mean, a lot of people think that, in interpretations of probability theory, there are Bayesians and frequentists. And so if you were, you're anti-Bayesian, then you would want to go with the asymmetric setting because you're not assuming any prior probabilities of the state's row and sigma. When we discuss, so there are problems. Okay, so in quantum information theory, you can solve the capacity problem, and then once you do so, you can start considering refinements of it, like how fast does the error decay to 0, that kind of thing. And the quantities that emerge there can be related to Chernoff divergence. And so I don't know if there's an argument that it's any less fundamental. And then you can recover the capacity in terms of these information that measures related to Chernoff divergence. So, yeah, I think that's all I have for you. Any other questions? Okay, so we're going to move on to trace distance and fidelity, trying to understand them in a fundamental sense. Okay, so we'll call this more distinguishability measures. In some sense, we've already connected trace distance to something operational, right? In symmetric hypothesis testing, last time we showed how the minimum error probability can be rewritten in terms of trace distance, right? What we showed is that the minimal error probability with the prior probability set to 1/2, the state's rho and sigma, this is given by this expression. Right? So trace distance is a so-called one-shot distinguishability measure. Right, because it's the experiment you think of is that a single system is prepared as rho or sigma, and you have to guess which one is which. You have a certain error probability, and the error probability is fundamentally linked to trace distance. The quantum Chernoff bounds and the quantum Stein's lemma, they show that Chernoff divergence and quantum relative entropy are asymptotic measures of distinguishability. I realize there's another important point I want to make. Sorry about this. I want to go briefly back to quantum Stein's lemma. This is a pretty important point. I want to show you how we can very easily get a proof of data processing for quantum relative entropy from the quantum Stein's lemma. So this is what we show. We're going to assume that we have this, okay? And now we already argued based on intuition that data processing inequality holds for hypothesis testing relative entropy, just from the operational task. Okay, so now armed with this, can anyone tell me why quantum relative entropy obeys data processing? All right, so you said this. And what? All right. Road sensor at? Right, you want to write road sensor at? All right, thank you. And then same group. Yeah, that's exactly right. So maybe saying, okay, now physically what we're doing is to the n copies of the state, applying the IID channel. And big N tensored little n times, right? We're applying the same channel to each state. We're just invoking this, okay? And now we just divide by n and then take the limit. And then this allows us to conclude data processing for quantum relative entropy. So that's a core statement in quantum information theory, first proved in 1975 by Wilde. And by now there are many different proofs known. This proof was discovered in 2012. Okay, that's all I wanted to say is that now, in some sense, we have data processing for quantum relative entropy. Okay, just to remind you about trace distance, it's induced from the trace norm, which is defined like this. Also the sum of the singular values of A. Okay, I want to tell you about a different interpretation of trace distance, different but related. Okay. So suppose in a protocol rho is the ideal state to generate. But instead, generate sigma. So in a single shot, what can you do to learn about the outcome, the output of the protocol? You can do a measurement. Right? You're trying to like assess how distinguishable rho is from sigma. So you perform a measurement. And it'll be described by a POVM with measurement operators mx. Okay. In the case that rho is prepared, the outcome, the probability of getting outcome x that's given by the Born rule, trace of mx rho. And then similarly, in the case that sigma is prepared, this is your outcome probability. Sigma. Okay. And then if you want to quantify the error between these outcomes, you could look at the absolute deviation, the maximum absolute deviation between these probabilities. Okay? And it would give you a sense of like, you know, well, how different these outcome probabilities are, right? I mean, to say it simply. So we take a maximum over x, trace of mx rho minus trace of mx sigma. Okay. And you could say, oh, okay, this will be my measure of error between rho and sigma, my measure of distinguishability. We came up with this by looking at a particular measurement. Right? We first said, let's fix this measurement and then maximize the error. But we might be interested in like how much they deviate under all possible measurements. Okay. And so the theorem that we get, or another interpretation of trace distance, is that this normalized trace distance is the maximum absolute deviation outcome probabilities with respect to all possible measurements. So this is the statement. Yeah. How do you prove this? there's a lemma we proved the last time, and the proof goes very similar to it. You know. The measurement that achieves this is the projection onto the positive eigenspace of rho minus sigma. And so, so that we talked about last time, and the proof of this is exactly the same. I just wanted to give you this as a different interpretation of trace distance from the hypothesis testing experiment. It's like the measure of error. Okay. This also, you can prove that the absolute values are not needed. Okay. And then when we have that, we get a semi-definite problem. So the trace distance can be written as a semi-definite program, which is nice. And it has an interesting dual, which is very simple. You take the trace, you minimize the trace over all positive semi-definite operators, where z is greater than rho minus sigma. And using our semi-definite programming tools, it's pretty straightforward to prove that. It can be related to the standard forms that we wrote previously. I guess we already showed it. I'll say it again. Trace distance obeys data processing. Technically, we haven't stated that. What we showed last time is that this minimum error probability obeys data processing. Error probability goes up in general if you perform a channel. But then there's a minus sign in front of the trace distance, so it flips around to this. The data processing, trace distance. And once you have that, like we said, you know, trace distance is a good distinguishability measure. Data processing. Okay, we hit the time. Let's just stop there. Any questions about any of this? We'll continue next time with trace distance and fidelity. But what I was saying here is really the main reason we use it. In a protocol like communication over a channel, there's an ideal state that will be generated at the end. And then we need some way to compare, you know, to evaluate the performance of the protocol. So we compare the output of the actual protocol versus the output of the ideal one using trace distance or fidelity. Those are the standard metrics used. And we'll be using those for all the communication protocols we study. All right, see you on Wednesday.